This video will be about exploring real numbers. So when we're looking at numbers, there's actually a lot of different groups of numbers. The first is called the natural numbers. Sometimes these are also called the counting numbers because they're the numbers you learn when you first learn to count. So 1, 2, 3, 4, 5, 6, so on and so forth. 1, 2, 3, keep going forever. That's all the dots mean. This keeps going in the same pattern forever. We also have whole numbers. They are very similar to the counting numbers, except now they include 0. So 0, 1, 2, 3. So if I were to ask you to classify the number 3, 3 is a whole number, but it's also included in the natural numbers. Whereas if I asked you to classify 0, 0 is in whole numbers, but not natural numbers. So we could only use whole numbers so far to classify 0. Integers are again like the whole numbers, except now they include negatives. So all the negative and positive numbers are included. We can also look at rational numbers. Notice all our numbers have been nice, round, whole numbers. Rational numbers include all the fractions, everything in between 0 and 1. So fractions, there's actually a lot of different ways to represent a fraction. If you had the whole number 2, 2 can be written as 2 over 1. That can actually be written as a fraction. So 2 is a rational number because it can be written as a fraction, an integer, a whole number, and a natural number. 1.5 could be written as 3 halves, so it can also be written as a fraction. So decimals that stop or terminate are also really fractions, so they are rational numbers. If we have a decimal that repeats, goes forever, that can also be written as a fraction. So decimals that repeat are included in rational numbers. Finally, we could also consider square roots. If you have a perfect square, the square root of 25, remember square root means what number multiplied by itself equals 25. So 5 times 5 is 25, which means the square root of 25 is 5, which I can then write as a fraction. So perfect square roots are also rational numbers. If it's not a perfect square root, like square root of 24, there is no number that multiplies by itself, then we actually need a new category called irrational numbers. So rational numbers, along with fractions, we could also say integers. We could say decimals that stop, and decimals that repeat. And we could say perfect square roots. So irrational numbers are decimals that don't repeat. If we were to plug square root of 24 into a calculator, sorry, this got a little smashed together. I'm going to move it down a bit. So decimals that do not repeat. So they could just list out the decimal itself. clearly that does not repeat. There is a 5 that repeats, but it'd have to have a 1 after to be a pattern that repeats. So decimals that don't repeat. Square root of 24, if we were to plug that into a calculator, we would also get a decimal that does not repeat. And at first it may look like it's going to repeat, but then the next one is 794. Or there are some special numbers that they have found, like pi, that is irrational. Pi is 3.14159, and then it also keeps going forever. So now if I give you a number, you can classify it according to one or a couple of these sets. Let's say we want to classify -5 and say what set of numbers is -5 in. So natural numbers was our counting numbers. They didn't include negatives, so natural numbers doesn't work. Whole numbers included 0 and positives, but we need a negative, so that doesn't work. Integers is where we first start our negatives, so this is an integer. But -5 can also be written as a fraction, so it's also rational. So this number is classified as multiple things. Say we have 0. Natural numbers didn't include 0. Whole numbers included 0. Integers included 0. And rational numbers included 0. So again, it can be classified as multiple things. It's also possible that it just has one classification only. So this is not one of the counting numbers. It's not a whole number. It's not an integer, but it is rational. It is a fraction. So it is only rational. You can also classify ideas as numbers. So let me give you an example to make it a little clearer. The number of people you work with. Now when you're talking about a person, you can't have part of a person. You can't have 3.5 people or 2.47 people. So we have to stick with those whole type of numbers. So that leaves us with natural, whole, or integers. Now integers includes negative numbers, and we can't work with negative amounts of people. I can't work with -3 people. So that leaves integers off the list. Whole numbers, we have 0, 1, 2, 3 going on. So I can work with no people, or I can work with a positive amount of people, so we could include whole numbers. And natural numbers can also work because that's just the positive numbers. So whole and natural work for the number of people you work with. So the next part of this section is talking about proving stuff true or not. So it's hard to prove something true, easy to prove something false using what's called a counter example. And a counter example is just an example that proves a statement false. You only need one. There can be multiple counter examples, but you only need one, really. So with our counter example, first we need something we're trying to prove true or false. So let's say I have the statement, all animals with 4 legs are dogs. So that one I can think of a very easy counterexample. Cats. Cats have 4 legs. They are not dogs. So our counterexample is cats. Now there's multiple. I could have said opossums or raccoons or rats. Those are all things with 4 legs that are not dogs. So let's make it a little bit harder. Let's say all animals with 4 legs are mammals. Now all of the counterexamples we thought of are mammals. So none of those can work. I'm just trying to get rid of the semicolon. This needs to be a period there. But I can think of a reptile that has 4 legs, like a crocodile. So that's a counterexample. So counterexamples can just be used to prove something is not true. So a more math-related one, all rational numbers are integers. There are many counterexamples we could use. I'm going to say 2.1. That is a rational number, but it is not an integer. So next, we talk about how to compare numbers. So when you are comparing numbers, we need a few symbols. We have less than or equal to, equals, does not equal, greater than, and greater than or equal to. So when you're comparing numbers, it can be helpful to have a number line available, or draw one out. Because especially the negatives can be a little bit difficult to figure out which one's greater than or less than when you're comparing them. So for example, if we were comparing -3 to -2, since -3 is further to the left on the number line, it is smaller than -2. It is less than, which is weird because we know 3 is bigger than 2. So that weirds us out. But when they're negatives, -3 is actually smaller than -2. So if we were to compare 3 to 2, 3 is bigger than 2 because 3 is to the right of 2 on the number line. And notice if I switch the order of the numbers, the symbol switches, less than. If we're going to compare some fractions, it usually helps to write our fractions as decimals. So -1/2 compared to -1/5. If I write this as a decimal, we have -0.5, and -1/5 is -0.2. So if you were to put this on a number line between 0 and -1, -0.5, that's halfway. -0.2, that's just a little bit, and I'm going to have to put it above because I don't have any room down here. So -0.5 is to the left of -0.2, so -0.5 is less than -0.2. We could also order from least to greatest, or greatest to least. So some of this list is already a decimal, some of it is not. So we need to change the fractions to decimals because those are much easier to compare. So negative 2 over 15 is the same as negative 0.13 repeating. The 3 only is repeating, so that's why the line is only above the 3. Positive 5 over 7 is 0.0714. 28. This one's a rather long decimal because it terminates, so I want to show every single digit. 57143. No ellipses come after because it doesn't keep going. That is the entire decimal. So now we compare. We also have the negative 0.58, negative 3.7. So negatives, the biggest negative number is actually the smallest number on the list. So negative 3.7 would go first. That's off our list. We've used it. Now we have two negative numbers left. Between the two, negative 0.58 is bigger, so that comes next. Then we have negative 0.13 repeating. Then we go to our positive 0.71428571443. So that is our list of numbers from least to greatest. You may have to put them back in their original form, so we know negative 0.13 repeating was really the fraction negative 2/15, and we know 5/7 was really the positive decimal. This section has covered quite a few topics, but there is one more called absolute value. So the absolute value of something is the distance a number is from 0. So if we were to look at the number line again, and we were looking at positive 4. Positive 4, comparing it from 0, we go 1, 2, 3, 4 spaces. So it is 4 units. Let's look at negative 4. Comparing from 0, we go 1, 2, 3, 4 spaces. So it is also 4 units. Now it wanted the distance. We don't care if it's positive or negative. We don't care if we went to the right or to the left. It just wants the distance, and the distance can't be a negative number. So absolute value ends up coming out positive every time. So when you use absolute value, the symbol is 2 bars around the number. So absolute value of positive 4 is 4 because it was 4 units from 0. Absolute value of negative 4 is also 4 because it was also 4 units from 0. So our answers always come out positive. One of the things that people do most often to make a mistake is they take a positive value and say, oh, I've got to change the sign to negative. That is not what absolute value does. It keeps something positive or makes it positive. If we were using 0, 0 doesn't have a sign, but so absolute value of 0 is just 0. If we were to do a decimal, it follows the same rules. Keep it positive or make it positive, so positive 2.7 would be the answer. And if we were working with any size number, we follow the rule of keep it positive or make it positive. In this case, we have to make it positive, 156. So that covers all the topics of this Exploring Real Numbers section. We went over the different groups of numbers, natural, whole, integers, rational, irrational, and what set you would put them in. We went through counterexamples, something that proves something is not true. We went through comparing numbers, looking at less than, greater than, or equal to. And we went over absolute value. So that concludes our discussion on exploring real numbers.